For assignment D1, we have the following learning objectives. We're going to determine the linearization and differential of a given function. These are going to be some keywords. I want to make sure we understand. And we're going to use linearization and or the differential to solve an application problem by selecting an appropriate model, using linearization and or differentiation on the model to solve the problem, and interpreting the solution in context. So the advice for mastering these learning outcomes is the important thing to remember about linearization is everything in this section comes from the tangent line. So the point slope equation of a line with slope m through a point that we've all learned and seen a bunch is that y minus y1 equals m times x minus x1. The tangent line is the point slope equation of the line, but now instead of m, we write it as the derivative at a, and the point we now describe as a comma f of a. So we will most likely not be giving you the full point up front. We will be giving you an x value, and you have to find the slope and find the y value. So these are equivalent formulas with those two things, or three things, excuse me, replaced. Now we're going to take this expression and modify it further to then form the linearization equation. So here's our tangent line. If we solve that previous equation for y, and so what that means is we take the f of a here and we add it to both sides, we get this as our result. Then this new equation is called L of x, and L of x, capital L, it just stands for linearization. So what we use with this tangent line, our new form of the tangent line, is we're going to use the linearization to predict or estimate multiple values of the original function. And when we do that, we use an approximation. So let me draw a rough sketch of what this looks like. So if we have a graph, f of x, and at some point on our graph, this is going to be a comma f of a. If I sketch a tangent line at this location, this line, which it's still a tangent line, but we're now going to call L of x. So as long as I'm near the value of a, the values that I get from the line are pretty close to the values that I get from the original graph. If we get too far away from a, we can see that the line and the graph start separating. So the distance, the vertical distance from the graph to this line, this is called the error, right? This is how far off the actual value of f is from our tangent line. So that's why it's very, very important that when we come to our conclusion, any values that come out of the line, we say that they're approximately equal to the value you would get on the graph. So there's a very big difference between an actual equal sign, we're saying they're truly equivalent, and this little squiggly equal sign saying it's approximate. We know it's not exact, but it's close. If we move too far away from a, right, we see that the linearization is generally useless. So in this picture I've sketched over here, the line's not doing us any favors at all. So what we would do in that situation, if I needed to know something about f of x up here, I'd pick a new value a, I would sketch a new tangent line, and then I would use that line to find values in that area of the graph. So the differential is going to evolve from our tangent line. So if I take, once again, the original tangent line in point slope form, and we rearrange this, so x minus a represents the change in x, so we're going to call that dx. So this part of the graph, or excuse me, equation, becomes this part of the equation. Then y minus f of a represents the changes in the y value, and we're going to refer to that as dy. So y minus f of a, those are the changes in the y values, and that's going to now be referred to in notation as dy. So we can see that this is in fact the same equation, we've just now changed the notation. So instead of giving you two separate locations and having you calculate the difference outright, we can now just give you the difference or the error between the two numbers, and you can pop it into the differential equation. The differential is useful in situations where you want to approximate the change in your function. So we don't necessarily need to know what the raw value is, but I want to know how far off is my answer from the answer that I would have gotten from the original function. So another way to think about this is the error, right? That's what we would call it in statistics or in physics or maybe even some engineering courses. We would talk about the error rate. We need to know how far off are we. So it's often useful to think about the differential as allowing multiple different values of a. When we think of the differential as a function of x, we write it in the following way. So if I have a function f of x, I write the differential as df equals f prime of x dx. So this notation is applicable for any named function that we have. So if I have a function a of x, so I might be measuring area, then the differential would be written as dA a prime of x dx. So d, name of function, derivative of function, d, input variable. So if I had a function, for example, that may be s of y, right? It could be something maybe measuring the surface area and the variable happens to be called y in this case, then the differential would be ds s prime of y dy. So function, name, input variable.